Hello. Today we're going to be talking about the Novel Enhanced Quantum Representation for Digital Images, or NEQR. Our team consisted of me, Kyle Johnston, Dennise Gonzalez, Jocelyn, and David Parkter. Now, you may be wondering, why would I want to use a quantum computer to represent digital images? And to answer that question, we need to look at the larger picture. A very important branch of information science is digital image processing. This is when an algorithm is used to process images, for example, satellite data or X-rays. These algorithms can be used for many things such as pattern recognition or edge finding. As our image and sensor technology has evolved, we now need to process more and larger images. This can begin to cause time problems for classical computers. One possible solution to this is quantum image processing. Now, in order to process images using quantum computers, the images need to be in a quantum state. This is what NEQR is used for. It transforms an image like this simple 2x2, for example, into a quantum state where it can be stored and utilized by other quantum algorithms.
All right, that's cool, but how do we get there? So in this the 2x2 image, we have each pixel that can be represented with a color and a location. The color is a simple 8-bit binary string, and the location, in this case, is 2 qubits for the row and the column. So we need this coordinate because when we're measuring a register of qubits, we're measuring one of 4 possible states. So we need to know which state we're in, or which pixel we're looking at when we measure it. And this index qubit array allows us to do that. And we can do this with images of a larger size as well. So 4x4 and 8x8. And we can do that when we need q, which is the grayscale range, the grayscale number of qubits, plus 2n, where n is the size 2 to the n size image. And in this case, we need 10, because 8 plus 2 to the 1 is 10. And if we measure this, well, we expect these 4 results, and that's what we get, each with about a 25% chance, as we expect. But this is in a noiseless simulation. So let's see how it would actually look on a real quantum computer with all the beautiful noise. And it's a lot. It's a lot of error here and here. All these values are values we don't want. But we can see that the values we do expect are still pretty common. They're way more common than the error. And this is just a limitation of quantum hardware right now. And the bigger the image, the worse this will get, which is why this isn't necessarily completely practical.
Here's a practicality test for our algorithm. We tested up to a 16 by 16 2D array which represents an image. We tested using Qiskit and a fake Montreal machine which simulates a real quantum computer. As you can see, the circuit creation time is quite short, whereas the compile time is really long and increases exponentially as seen in the graph. The width, or the amount of qubits needed to run the algorithm, does not increase exponentially. However, it is quite a lot of qubits, especially since the maximum amount of qubits a quantum machine can process is 65 qubits. The depth, or the amount of quantum gates needed to run our algorithm, also increases exponentially. Because the depth and compiling time increase exponentially, this poses a huge problem. If we wanted to process an image with hundreds of pixels, it would take way too many qubits and way too much time. As such, for any QR to be practical, we need hardware with lower error rates, more qubits, and theoretical pieces of hardware such as quantum RAM to speed up compile time. If we can make any QR practical, we can use it in things such as quantum edge detection of medical images.
We faced some challenges throughout our project, starting with our initial research. When reading papers, we encountered lots of long and confusing equations. These equations also contain some symbols that we had never seen before. Luckily, the papers did provide a few explanations for us to understand the equation better. We also did some separate research to find additional information, and we found the Qiskit textbook to be really helpful in explaining the algorithm in simpler terms. Another challenge was that most of our literature we went through explained the algorithm implementation in 2 by 2 pixel images, which are way too small. We needed to code an algorithm that would work on any image size, which was a really hard challenge. But we did end up figuring it out. Aside from the aforementioned challenges, we also encountered issues with our coding. The grayscale values for each pixel are supposed to be converted to binary, and these values can be read from left to right or vice versa. For some of the portions of our code, these binary numbers were required to be in Big Indian. When we were running our code and debugging, we noticed our tests were failing and didn't know exactly why, so we made sure our thought process was correct. At the end, we realized that our values were just being flipped due to them being in Little Indian instead of Big Indian. Despite this being a small issue, it did take us a long time to figure it out. And here are our references and sources. Thank you for listening.